So I was in the car with my dad the other day, and he mentioned this thing called a pop boat. And the way he described it was he'd seen a YouTube video where a guy had found a tin can, cut it up, run a couple of tubes out the back, mounted it on a chassis, and when he placed it in the water and lit a candle under it, it was able to propel itself. Right, so this sounded really, really cool, and so I googled it, and turns out it's a toy. It's a really common toy, seemingly in India, but the main body of enthusiasts seem to be in France, and it's apparently patented in America. So it's an odd distribution, but it's a really simple little thing. So I ended up making one. They're not hard to make. You can find tons of tutorials on how to make these. So you've got a tin can there, which I've cut up and used for the boiler. There's a candle for the power supply. It's just a juice carton that's been cut up for the hull. And there are two straws, which are providing the flow from the boiler to the back of the boat. So made it, myself and Megan, we launched it in the bath, and it worked for a bit until it caught fire. And we had to take it out and extinguish the blaze, and we patched it up and stuck it back on the water, and thankfully this time it worked. So it was a really fun little exercise, but it's also just as a toy a really interesting piece of kit, because it touches on a couple of different areas, from fluid mechanics and physics and engineering. So, and the more I kind of read about it, the more interesting it became. So I just thought I'd kind of make this video to sort of tie the whole experiment, the whole project really together, and then that way I can call it finished and I don't have to think about it anymore. I mean, the first thing that's really interesting about it is the engine itself and the mechanism by which it propels itself. So the propulsion mechanism is basically comprised of the boiler, the two straws, and the candle. And the boiler's hollow, and to begin with, what we do is we inject some water into it. We then light a candle underneath it, and the candle heats the water, and the water produces steam, and that steam enters the tubes and helps to power the boat. But this isn't a steam engine, right? In a steam engine, what happens is we boil water and we produce steam, and that steam drives a piston. There are no pistons in this. There are no moving parts at all, which is one of the things that makes it really, really unusual. So you can describe this thing in detail basically in terms of two strokes. It's essentially a two-stroke engine. At the beginning of the first stroke, the tubes are full of water, and there's some amount of water in the boiler. There's also air, and the air is important. The candle heats the water, and the water produces superheated steam, which results in a huge increase in pressure inside the boiler. So this steam expands, and it forces its way down through the tubes, and it pushes water out behind the boat, and that's what propels the boat along. But then what happens is, as the steam moves through the tubes, it cools and it condenses back into water. And this causes it all to contract, which results in a massive drop in pressure. And because there's now a drop in pressure, and the pressure outside the boat is greater, or outside the boiler is greater than the pressure inside the boiler, it sucks water back up and returns to the top of the first stroke. That sucking motion is essentially the second stroke. So we're never going to run out of water. Under ideal circumstances, for as long as the candle burns, the engine will run. So the propulsion mechanism by itself is pretty interesting, but it also raises a question. If you have a method of propulsion which is exhaling, blowing out water to move forward, but then has to suck water back in order to begin the next phase, well, shouldn't the boat remain stationary? Because the effect of drawing water in is going to cancel the effect of blowing the water out. So why does this work? And it turns out this is actually a pretty old problem. It's fairly elementary, and you find it in physics textbooks at a beginner level. But it's still something that people find quite interesting. And it's actually analogous to a thing called the Feynman sprinkler problem, where the question was asked, if you had a sprinkler which sucked in water instead of blowing it out, would it still rotate? And the answer is no, but the question is why. There are loads of papers which talk about this from various different perspectives. And there are people who explain it from the perspective of fluid mechanics and try to build models which describe it. There are people who use just the laws of mechanics, the basic laws of mechanics. But in general, they all arrive at the same really simple analogy, which is the boat moves for the same reason that you can blow out a candle, but you can't extinguish it by inhaling. So when you blow, you focus air into a specific stream. But when you inhale, you're drawing it from all directions, and it's the same situation with the boat. It exhales in a very direct stream, but it inhales from all directions, and that's what allows it to move. So the last question which sort of sprang to mind for me, and maybe it's the computer science roots or whatever, I don't know, but the last question was basically how efficient is this engine? So given that we have to put a certain amount of energy into the system, how much of that energy is converted to motion and how much of it is lost? Now you have this in any engine that you deal with. So for a petrol engine, about 35% of the energy in petrol is actually converted to motion. For a diesel engine, it's about 40%. For a hydrogen fuel cell engine, it's about 60%. And for an electric engine, it's something like 97%. But that doesn't account for how much energy is actually spent generating the electricity in the first place. Now, I can't guarantee the accuracy of those numbers. I pulled them really quickly off Google. But our little engine here, it's about 1% efficient. 1% of the input energy is converted to motion, and the rest is lost through heat and noise and various other things. So it's essentially useless for anything other than a toy and to explain some physics concepts. So this was a really fun little project. It didn't take me very long to build the model. It only took about an hour, and that was mostly because it was my first time building one, so I was being cautious. It's cheap, it's built from household materials, and it's a really fun way to demonstrate some really simple concepts. I've touched on a few really brief things in this video, but the amount of literature out there is huge. People have tried to compute the maximum efficiency of the engine. As I've said, it's patented. The whole design is actually patented by a guy in America, or it was in 1916 and 1926. Those patents have expired by now. It's well worth investigating, just for your own personal enjoyment, and it won't take you very long to put it together. So cheers folks, that was basically a rant at a camera to explain my weekend.